here is the outline and summary for my today's talk. So in today's talk, I want to show that there's a special class of the fermionic HPD. It's called supercohomology HPD, can be dualized into the bosonic HPD. It's called Twogroup. So basically, I will first define what's the topological symmetry protected topological phase, and what's the meaning of this word supercohomology. And given this supercohomology phase, how do we bosonize into some bosonic theory? Then we move to the other side. So I will introduce what is the definition for the Twogroup. People may not be familiar with this Twogroup symmetry. And I will introduce how do we gauge in the one-form symmetry of the Twogroup to get the bosonic theory. So from fermion side, we can go to the some Z2 gauge theory. And from the bosonic side, we can also go to the Z2 gauge theory. So this can like apply the mapping to the same bosonic Z2 gauge theory. So which provide the duality between the bosonic phase and fermionic phase. Yeah. So first, let me describe what's the definition for HPD phase. So when we talk about HPD, we always consider zero temperature. So we focus on the ground state. So we want to say a ground state is equivalent to other ground state if they can be connected by the local unitary symmetry operator. So here the symmetry is a constraint. So if we don't have any symmetry, our classification is larger. So if we put a constraint here, so we require each local piece to be symmetric. So we can divide the phase diagram into a more like smaller region. So here the symmetry protected topological phase means we require symmetry, and we study how the ground state of 1, 5 can be connected to each other. So so if the two states are in the same phase, if only if they can be connected by the finite depth. The finite depth is very important. The finite depth quantum circuit in this form. So there are many well-known results for how do we classify the fermionic HPD phase. I think the most clear construction is from the Chen Wang and Chen group in their recent paper. So they showed that for arbitrary dimension. So in this talk, I will focus on 3 plus 1D. The 3 plus 1D, the complete fermionic phase can be constructed in this following way. It's called decorated construction. So first, we put a G spin on the vertex. Then we can put a complex fermion at the center of tetrahedron. So this blue dot here is the complex fermion here. And then we can decorate the P plus IP superconductor on the domain wall. So consider, for example, G0 and G1, between there's a domain wall. If G1 is different from G0, there's a domain wall, and we just put the P plus IP on this closed surface. And then we can also decorate the key-type chain on the closed loop. So for example, if I go along this red loop, and if on a closed loop, we can also put the key-type chain on this closed loop. So it turns out to be this construction is complete. So it requires 3 layers. So we can put the complex fermion, we can put the P plus IP, and we can put the key-type chain. So in this talk, I will only focus on the first part. So I will only decorate the complex fermion in the center of tetrahedron. And this is called supercohomology phase. So when people say supercohomology, you should have the picture in the mind. It's like you have the group element on the vertex, and you have the complex fermion in the center of the tetrahedron. So actually, the fermion decoration is a function from the G to the 4th to Z2. So it depends on the G1, G2, G3, and G4. And this function though return the value 0 and 1. So 0 means there's no fermion inside, and 1 means there's fermion inside. So it's like given the spin. So here G1, G2 can be like a Z2 spin or arbitrary group. So given a spin configuration, with this function, we can know there's a fermion occupied or unoccupied here. So this is the setting for the supercohomology phase. So he has the G times Z2F symmetry. So the G symmetry is just a usual symmetry. We can multiply the group element G on every vertex. And the Z2 fermion symmetry is just a parity. It's product of the fermion parity for each local site. So here T means tetrahedral. So it's a product of the fermion parity on the whole tetrahedral. And then this is the total fermion parity. So this is the our Hilbert space for the supercohomology fermionic theory. And now let's introduce how do we bosonize it. So first we go to the dual lattice, and here I just use the cubic lattice for it's just an example, but it can work for arbitrary triangulation. So here, because we go to a dual lattice, our fermion originally is in the center of tetrahedral. It becomes a vertex here. So in this dual lattice, we have a fermion at each vertex. And then we can define the fermion parity on each C. So each C is the vertex here, and the fermion hopping. So fermion hopping is the gamma at one side times gamma prime at the other side. So we want to map these two kind of generate into the Pauli matrix. It turns out to be there's a very nice construction for Pauli matrix. So here we put a Pauli matrix on the link. So we can define some hopping term. For example, this blue hopping is the X operate on the 1 and the Z operate on the 3 and 4. It's X1 times Z3 times Z4. So the way we define it is we draw this blue line. It's called framing, and we find this blue line intersect with this link 3 and link 4. So we define this X1 times Z3 times Z4. So similar for example, this red line is the X at 3, sorry, it's X3, it's typo here, times Z5 times Z6. So we can define this hopping in this way. So we can show that this kind of Pauli matrix has the same fermionic statistic for the fermionic hopping. So we can make the fermionic theory into the Pauli matrix. But it turns out to be there's a more constraint because this kind of hopping, they are not independent. So if we consider we hop a fermion around a closed loop, it will return a gamma A squared times gamma B squared times gamma C squared. So it turns out to be 1. So we need to impose this constraint. Because if we use this dictionary, we map this hopping term and the parity term into the Pauli matrix, and we want this term to be 1. So here is our gauge constraint. So gauge constraint is the X operate on this red square times this Z operate on this blue dot. So at the end, we can map any fermionic theory into a Z2 gauge theory. So you should just treat this as just some Jordan-Wigner transformation. So given fermionic operate, I can rewrite the model into the Pauli matrix. So here we can.
Question here. I know we're not supposed to, but I kind of can't watch without, Anyway, so it's Victor Golitsky. So yeah, I was just wondering. So usually when you do Jordan-Wigner, you generate all kinds of strings, right? Yeah. Which are kind of make the Hamiltonian totally useless and crazy unless in 1D. Or in some very special situations. So somehow here is not the problem.
Yeah, because so here we have this gauge constraint. So we can somehow cancel some string operate. So if we want to apply Jordan-Wigner in the 2D, we need to choose some path. So but in either way of the choice, there must be some hopping. For example, the nearby hopping. You need to go around some very long string, so which make the mapping non-local. But here we can try to map this fermionic theory into some gauge theory. So it's like we have additional gauge constraint, and this can make sure the mapping is local.
So when it's here, do you have like a Hamiltonian or something, some class of Hamiltonian? So what does it mean here, or where exactly? So what's the theory you start with? I'm not sure.
So here, so it doesn't depend on any Hamiltonian. Because here, any fermionic operator can be generated by these two types of terms. So it's fermion on-site parity and fermion hopping. So as long as your Hamiltonian contains the Chen, which is the even number of fermionic operator, you can rewrite into the function of these two generators. And we can map this generator into Pauli matrix. So it's so it doesn't depend on your, it works for any model. Like, so here is just like a mapping between the fermionic algebra and the Pauli matrix.
Since Victor Galitsky asked a question anyway, let me ask something that's I'm a bit perplexed about. And it's definitely my ignorance, and I'm not being modest in saying it's my ignorance. I had not been following this whole field because Mesam Barkash is next door. I just feel I can go ask him. So why would I want to map the fermionic theory into a Z2 gauge theory? I mean, I love fermions and I can do a lot with fermionic theory. Why would somebody want to do that other than the fact that there is some mathematical beauty in doing it? Is there a goal here, or is it more like?
I think one concern is like for fermionic theory, it's very hard to write down the partition function. So if we try to write down a partition function for fermionic HPD, you usually involve, for example, the Boltzmann integral and a Boltzmann variable. So I think people tend to try to write a Lagrangian into a more clean form. For example, just like a TQFT. Yeah.
Okay, so the goal then is that doing statistical mechanics down the line may turn out to be easier with the Z2 gauge theory rather than with the original fermions. Is that?
Yes, yes.
Goals? Okay, I just want to understand the broad question. Go on. I get the point. Thank you.
Yeah. So the principle here is just like we can map any fermionic theory into Z2 gauge theory. So this is work for any model. It doesn't depend on which model we study on. So we have completed the right-hand side. So given a supercohomology model, we have the G spin on the vertex and fermion in the center. We can map into the G spin on vertex and the Z2 value on each phase. So it's called a G-enriched Z2 gauge theory. Okay, now let's go to the left-hand side. The left-hand side is called two-group symmetry. So the formal definition of the two-group is quite scary. So it contains the G and A, both are group, and it contains a 3 cocycle, and it contains the automorphism of G and A. So please ignore the message here. So in today's code, we can just take the two-group symmetry. It's just a zero-form symmetry plus one-form symmetry. So the zero-form symmetry is just the usual symmetry. We apply the group element G and we multiply on every vertex. And the one-form here means the symmetry action is actually in the codimension 1 sub-object. So here's an example. In the 2D, we can consider any closed surface. And then we focus on the link which intersect with this closed surface. For example, here we draw a sphere here, and we consider the product of X around this link which intersect with this sphere. Because the sphere is 2-dimensional, and we consider our space is a 3-dimensional. The 2-dimensional sphere has a codimension 1. So this symmetry action is called a one-form symmetry action. So the two groups means we have the zero-form symmetry and we have a one-form symmetry. But there's some subtlety here. So I shouldn't use this plus here. They don't decouple. So when we apply the zero-form symmetry, we not only multiply the group element G on every vertex, we also modify. So here on the link, we have the Z2 value. So we also modify the Z2 value on the link. So this is the function is determined by this law. So remember the law in the fermionic case is the fermion decoration. But in the two-group case, this law is a 3 cocycle. It's a way how we couple the zero-form symmetry and a one-form symmetry. And it turns out to be if we couple them in the right way. So usually this function defined here, this theory can be mapped to the supercohomology theory. It's just kind of a magic. So we can somehow encode the information for the fermion decoration into the coupling between the zero-form G symmetry and the one-form A symmetry. Yeah, so without going to the mathematical definition, we can just take this as our definition for a two group. So we have the G symmetry action, is a usual symmetry action, times the one form Z2 symmetry here. So this is our two group symmetry action. And
I have actually a question also. Is this two group only, like, is there a more general definition, or because here you've defined it very specifically for this Hilbert space where you have link degrees of freedom and site degrees of freedom?
yes,
Is there like a more general definition of two group which doesn't depend on exactly what the Hilbert space is and this specific structure of Hilbert space?
I think that's a good question, because I think the two group defined here is called a weak two group. I think the weak two group and a strict two group, they are a little different. So like the weak two group is just the formal definition is how we extend the symmetry. So for usually if we have the two co-cycle, this describes how we extend the G symmetry by, we have the group A and we want to extend by group G. So we use the two co-cycle. But here, if we have the three co-cycle, it's called cross module. So given the G, and we want to extend by A into a cross module. So yeah, I don't have a formula here, but I can describe to you later. So because if this is two co-cycle, this data is simply just how we extend the G by A. But here the three co-cycle, it becomes we extend the zero form G symmetry by one form A symmetry. So actually this Hilbert space is not spatial, it's the classifying space for the two group. Yeah, so if we only have the symmetry group G, we only have the group element on the vertex. But if we consider two group, the classifying space also consider link degree of freedom. Yeah, so actually this kind of picture actually comes from the definition of two group. So it's not a spatial case. Okay, I can answer to your question later in more detail. Yeah, sorry about
the discussion.
Yeah. Yeah, and so how many minutes? So let me finish it quickly. So in the last step, we want to map these two groups HPD into a gauge theory. So the way we perform this is called gauging one form Z2 symmetry. So on the left-hand side, we have a Hilbert space with the Z2 on the link. So on each link, we have the Pauli matrix. On the right-hand side, we have the Pauli matrix on the face. So on the left, we have the one form symmetry. On the right, we have the gauge symmetry. The gauge symmetry is just product of Z on tetrahedral equal to 1. So it turns out to be, if we count the degree of freedom, the number of the dimension of the space equal to each other. So actually, consider the configuration here. We can make from this configuration, this is called A. So we have the 0 and 1 on each link. We can map to the right-hand side. We have the 0 and 1 on each face, according to this mapping. So basically, this dot here is just summing over the three links nearby. So here we have 1, 2, 4, A12, A24, and A14. And this dot is just summing over these three values. It turns out to be this mapping gives the complete duality for the left and right. So this is very similar to the 2D Kramer-Wanier duality. So yeah, so we can, so I don't, due to the time limit, I cannot start from the 2D, but it turns out to be, it's quite similar. So let's give the duality between this one form symmetry space and this Z2 gauge theory. So from left side, we have this two group Hilbert space. We can map to the Z2 gauge theory. So if we design our model carefully, we can measure they coincide in the middle. So it's like we have some two group map to the Z2 gauge theory, and we have some supercohomology phase, which also map to the same Z2 gauge theory. So this kind of mapping can provide just the duality between bosonic HPD phase and the fermionic HPD phase. And yeah, so due to the time limit, I just gave the two examples because the formula is horrible. And finally, I want to thank to my collaborator. So here is Tyler Ellison. He's a student of Lucas Fikowski. And this is Ned. So he's a student of Ashwin Vishwana. And he's my advisor. And yeah, so I just stop here for and will come in for any question.
Yeah, thank you. And now it's open to questions.
I have a question.
Yeah.
It's about your definition, the definition of a group supercohomology phases. So in terms of a triangulation, you had said that you place group elements on the vertices of the triangulation, and if they satisfy a certain condition, then you place a fermion at the center. So how do you understand this statement in real space? So how do you identify this fermion? Say, if you are actually doing symmetry operations.
You mean real? What do you mean by real space?
So if you have a physical state, what does it mean to place like a certain configuration of group elements like this, in the sense of detecting a response or something like that?
You mean what's the physical meaning of this G? Is your question?
I'm asking, so what is the like how do you detect this fermion?
You mean physically detect or theoretically?
Well, yeah, like how do you do a thought experiment to detect this fermion on a physical state?
Yeah, so I think the most physical one is called symmetry fractionalization. It's this law. So consider the symmetry flux. So we first gauge the fermion parity and we install the flux. So if there's a non-trivial fermion decoration, so after we install the flux, we can observe the symmetry fractionalized at the boundary. Just like in the 1D case, in the 1D key-type Chen, we have some Mairana mode on the end. So it's a signature for the symmetry fractionalization. Or you can think of a Harden Chen. Harden Chen is spin 1, but you can also observe the spin 1/2 at the end. So same thing here. It's like we get the fermion parity and we install the flux, and we can see the symmetry fractionalized at the boundary of this. It's called, so we insert flux is a closed loop boundary, and then we can observe the symmetry actually fractionalized. So I think it's one of the most important feature for the HPD phase.
Is there any question?
Yeah, I can ask one. Do you have any comments on how you might extend this, if there's any sort of an extension to when the symmetry group you're starting with is not just G cross Z2F, if there's some more complicated group extension?
Yeah, that's a good question. So originally I considered our GF is just G times G2F. But it turns out we can consider like the non-trivial central extension. So based on this, I think the first thing to do is we modify the Gould equation. So the supercohomology data will include another, it's called two-core cycle, because this extension is determined by two-core cycle. And we must include this two-core cycle into our construction for this our two group here. So I think we have made some like a guess. So it turns out to be, we can write down alpha 4 is the two-group cocycle, which corresponds to the non-trivial fermion extension. But I think there's some subtlety, like about how do we show that they are equivalent or not? So if we consider this extension, the equivalence relation for the supercohomology also change. I think we cannot show that different data correspond to different two groups. That's the issue here.
So sorry, just to make sure I've understood what you said if you input different supercohomology classes, you might be getting the same two group with the construction you have right now?
Yes.
Okay, I see. Thanks.
Is there any question? Oh, we still have some time. But if there's no question, then we can keep the schedule on time, actually, because you start like 5 minutes late. And thank you, Yuan, for your interesting talk.
Thank you. Yeah. Let me stop sharing.
Yeah, please.
How do I do that? Okay, I find it.
Okay. And Jay, you can start share.
All right.
So our next speaker is Jay Sao. He's a professor in Maryland. I think I don't need to give an introduction. Today he's going to talk about on the theoretical ability to identify topological wires based on transport measurements of 3-terminal and Coulomb blockade devices. Jay.
All right, thanks. Can everyone see, can you hear see my screen and hear me?
Yes.
Yes.
Okay, excellent. So yeah, so just briefly, I mean, yeah, this is the title of my talk, and it's basically work on Mairana nanowires done with Haining Pan and Yuhua Lai, and in collaboration with Shankar. Actually, there are two reasons why I'll spend most of my time on this work. One is that, well, I recently gave a talk at Microsoft, at a Microsoft meeting on this. So I had this talk ready, and the work is recent, and it involves talking about work from 2 other students in the group. But also, but before I do that, I wanted to give a brief summary of, or spend a few minutes introducing other work that's done by collaborators at CMTC. So for most of these, the idea, the hope is that that I'll get interest and feedback from others and possibly collaboration from others in CMTC. So the first topic, which is work that is in preparation with Huang Kwang. This is close to done, but in the writing stage. Is a question of we wanted to, motivated by Kapitulnik experiments and from a few years almost ago on heat diffusion. They found that in some sense, and this, I should put this phrase sub-Planckian in quotes because as lots of people here will attest, it's not clear what it precisely means, but in some sense it's quite low. We looked at the possibility of just phonon dynamic, or if you have an insulator with no active electrons, if you have a very complicated phonon system, like complicated lattice, like most of these systems are, whether you can get very low heat diffusion, and we find indeed we can, and in fact we can get a situation where what's shown here is the Green's function for the acoustic phonons, like basically turning into featureless mush above some frequency. So the temperature is high, you get very low diffusion. Another topic here that is much on the right, that is much less in preparation. It's only preliminary work that Yang Zi and Risheng we started together, is talking about the so-called Callan-Harvey mechanism in axion insulators. So axion insulators, again, it sounds fancy and pie in the sky, but actually work with Beta and Roy, who used to be a postdoc here at CMTC in 2015. We did something which to me actually at that point sounded crazy, which was that if you applied a magnetic field, then you could get an enhanced magnetization induced gap opening in wild materials. And that's what we called an axion insulator. And it seems that Claudia Felser's experiments are seeing something along the line. So inspired by that, I've been trying to continue along those lines with Yang Zi and Risheng, and I'm happy to chat more. Another topic that I have interest in is Mairana's from iron-based superconductors. And iron-based superconductors are basically, in some sense, one of their surprising properties turns out to be that they are a layered topological insulator, but except that it seems that only in a very narrow region of doping, like between selenium and tellurium composition. So we're looking at all of possible composition fluctuations and whether you can get like topological states like this, like the surface state, meandering between blue, which is topological, and islands of orange, which are non-topological. And sort of in a, I guess with a slight feeling of guilt given Shankar's introduction of the absence of cold atoms, I have a little bit of underground cold atoms still going on. And this is work as a follow-up with, again, with Will Cole, who used to be a postdoc here, on these 1D gas, both gases with double minima, which can happen in either higher band systems like Chang-Chen's group or flux ladders in Spielmann's spin orbit gases. Again, here it's unclear where this will go experimentally, but again, I can't. But theoretically, at least, there seems to be a Lifshitz quantum critical point. Chang-Chen thinks that he saw it, and there's hope that we're studying, like basically understanding if there's any more interesting signature of quantum critical dynamics that someone could look for here. Anyway, with that, I'll go to the main part of my talk, which is the Mairana system. And again, I'm not going to attempt to explain very much. I'm not going to be as brave as Yuan Chun was, but instead I'll sort of try to give you a flavor and then you can ask more questions or discuss. I'm happy to discuss with what interests people more. So, so again, just preview. I mean, Shankar actually showed one of my first talks in this subject back 10 years ago, and this subject is still continuing in CMTC and also in experiments. And part of the reason is that there is quite a bit of progress. So, I mean, following our theory work, people have made these beautiful devices with nanowires and aluminum shell superconductors. And they've seen zero bias peaks, which seem to be nearly quantized, as you see here, and that appear after a certain critical Zeeman field. And this is data from both Delft on the left side and Copenhagen on the right side. I'd say because of certain subtleties, these are almost quantized. And recently, there's also almost quantized conductance in iron superconductor. So this is there's quite a bit of experimental progress, at least. Actually, I'd say a lot more experimental progress being made in, well, at least in the past few years. We don't know where it's going next. Then in some sense, in theory. So, but the burning question that a lot of us at CMTC are interested in is this: does the zero bias conductance peak mean Mairana? And the short answer is no. There are at least two mechanisms. One is this random matrix theory in symmetry class D based mechanism, where if you have a disordered interface between a normal metal and a superconductor, you typically the propensity of zero bias peaks appearing at the as you vary some parameter. So this one doesn't look like the experiment, but variants of this actually, as I'll mention to you, can look like the experiment. And the other possibility is something that is similar to edge reconstruction from those of you who are familiar in quantum Hall. If you have a potential, again, near the end of the wire that changes slowly, so that in the bulk, you have the highest density, which is non-topological, and outside you have very little density, which is again non-topological, but in between you have a range of topological, then you can have a pair of Mairanas that are sitting at the same side. And that could, this non-topological in the bulk, but still looks like a Mairana. So these are the two sort of scenarios that we're worried about. So recently, another work from CMTC from Haining Pan and Shankar summarized this very nicely in terms of good, bad, and ugly. So so the good scenario, so in this nanowire, so good, bad, and ugly zero bias conductance peaks. And so the nanowire could be good, which means it has nice topological peaks, Mairanas, which have zero bias peaks at the end. It could be bad, which means that it has this soft ending where it's non-topological, but again has zero bias peaks at the same side, from Mairanas on the same side. And this is bad. And ugly is just that the wire is full of crap and you just have zero bias peaks by chance. And here are simulations, and they all look like, they all kind of look like the experiment. And actually, sometimes ugly or bad, as I'll mention, could look more like some of the experiments. Now, what do we do in terms of theory? Well, so the new experiments are again, progress in this field theory progress in this field really has to be closely tied to experiment, because that's where the real value is, in a sense. So the progress in terms of experiment is what's going on is they're going to more complicated setups where you have two probes, normal probes on the left and the right, and the superconductor is grounded. In that case, you can actually, there has been preliminary data measuring transport from the left lead to the right lead. And what theory shows is that in principle, there should be a gap closing that one could see at in that transport. So, and the other prediction, this is again, they're both from the Netherlands. You can get quantized heat conductance at these. So we wanted to examine these two. That was that was the work that we did in this archive work paper posted. And so in the to show the ideal case, things kind of work, but one worry is that this conductance is quite, the gap closing signature can be quite weak. So we basically looked at all the measured signatures, so local conductance, non-local conductance, thermal conductance, and and along with the topological invariant of the wire. So in the theory, you have the advantage that you can compute the topological invariant, which you can't do in the experiment. And so this case all works. The bad case works in between. Ugly case, it gets worse. But now let me get to the point, which is that the one that matches experiment most is this short and ugly case, where, you see a gap. You see basically with the, so this is the theory, but the experiment, I assure you can go and look for it from Copenhagen, looks kind of similar. You see a gap closure, but no gap reopening, or not a lot of signature of gap reopening. And in this case, we find theoretically, at least, the topological invariant is just not very well defined because the system's too short. Anyway, I have about 5-ish minutes left, so I'll tell you about the other piece of work shortly. And this is work done with Ihua Lai, who's another student. This is another kind of experiment, which is Coulomb blockade. So the Mairana wires have been put in the Coulomb blockade regime. This was actually done in 2016. And what you see is, so in the Coulomb blockade regime, you look at the conductance as a function of magnetic field on the x-axis and voltage on the y-axis. In the non-topological phase, you see 2 aperiodic Coulomb blockade oscillations corresponding to tunneling Cooper pair transport to the nanowire. As you apply Zeeman field, you see that this peak splits and it oscillates a bit, and eventually you get to purely 1 aperiodic oscillations. And if you look at the splittings, this was attributed to Mairana's, and by looking at a few points and few devices, it seemed like there was some kind of an exponential, but let's not talk very much about that. Similar data was, except for the exponential dependence, was seen in Delft. The basic theory for how this works is as follows. So I have this nanowire in the Coulomb blockade regime. And then I have 2 leads on the left and the right side, and I'm basically transporting current from the left to the right lead. If I have, and then what I want you to focus on is here, the diagrams. So what's plotted is energy as a function of gate voltage or gate charge. And for a certain charge state, you get a parabola. And what's plotted here, the 2 black the black parabolas are even charges in the island. So you increase the gate voltage, you get one parabola. At some point, you cross over and you favor, let's say, adding 2 more electrons to the system. And then you keep going. That's what gives you periodic transport at this point. But in a superconductor, you can also have this situation. This blue line is a state with odd electrons, and so it requires overcoming the superconducting gap. So that's where it's at higher energy. But as you apply magnetic field and you get subgap states, the state can close. And if you have a Mairana, then this becomes exactly degenerate, and you get E-periodic situation. So that's the basic understanding. But there's a lot of other information, like, for example, what is the energy splitting that you see are supposed to see? What is the amplitude that you're supposed to see in Coulomb blockade? What does that tell you about the state on? And those are the kinds of details that EWA's simulations intended to see. I should say, before going to Yua's work, Qingkai Chu, who used to be also at CMTC, we looked at this together. We looked at the splitting together before and found that, well, firstly, you can get similar behavior from not just Mairanas, but from Andreas states, which is the case, what was the bad zero bias peaks. The puzzle with Mairanas was that why did the theory always give splitting oscillations that increase, but the experiments show decrease? So Qingkai found that in some cases you could get it to decrease, and the length dependence was kind of all over the place. Now, with Ihua, this is work with preparation. What we did is we went a couple of steps further. So the main technical advance was that we managed to adapt the Coulomb blockade paper from Meyer and Wingreen to make it work for this system. And let me tell you the technical challenge here. So this seems like just a classical trans problem with probabilities that are all classical. Yeah, and this can be solved using a rate equation. But actually, what is not realized is that this rate equation formalism, just like actually the quantum problem, has an exponential complexity because the probability is a distribution in an exponentially large space, just like the wave function is in an exponentially large Hilbert space. It's exactly the same dimensional space. So rate equations are actually hard to simulate. But by making an assumption on equilibration, we get around this and manage to simulate this in order n. We also included, so if I go back to this picture, this superconductor has a self-energy, and we included that as a self-energy effect on the wire. So those were the two things, which was a lot of work, and you did that. So yeah, so we get preliminary data, again, that looks a lot like experiments. We can get, so our simulation really starts right around here, where the spectrum goes from 2, just where the 1E or the 2E periodicity breaks. So we get a very dark region right around there, and then a somewhat bright region, and then a very bright region. So with fiddling around with parameters like this one, we managed to get the intensity pattern to look a lot more like experiments. That's our main, that's the main thing we managed to do. Though for such systems, it turns out that the superconductivity, the topological phase, is very short. We also get the oscillations to decrease quite more generically when we include self-energy with magnetic field, just like experiments. So that works better. Anyway, so that ends my talk. This is actually a more technical summary that was meant for my Microsoft talk than this audience. So I'm not going to read it. I'll just leave it up there, and I'll just take questions. Thank you.
Thank you for a very nice talk, and now it's open to questions.
Can I ask a first question?
Oh yeah.
So what about the? I have a question on the Coulomb blockade, the self energy in the Coulomb blockade. So what's the form of the self energy as a function of Vz, the magnetic field?
Oh, it's this actually the. Oh, I don't think I have it here. It's the same one that I use. I don't have it here, but I can. Let me just. Yeah, I don't have it here, but if I can write it on a blank slide. But it's it should not be a surprise to you. So it's and I might get some of this wrong. You can correct me, but it's basically lambda times omega tau naught plus. Oh, sorry, that was not correct. Oops, sorry. Sorry, just a second. You know, that's actually correct. Delta tau x divided by square root of delta squared minus delta naught squared minus omega squared, and delta naught is a function of Vz, which is delta bulk times 1 minus Vz over Vc squared to the power half. I think that's correct.
Yeah.
Yeah, no, that's correct. Yes. Yeah. But what was your question then?
Oh, my question is just simply, since you know that the superconducting gap will suppress, would be suppressed as Vz the magnetic field increases. So, I mean, even there's no Coulomb blockade mechanism, the Mairana oscillation will be suppressed due to the suppression of the superconductor gap, right?
No, yeah, no, you're absolutely right. So I shouldn't say that we discovered this recently, though for the first time. Though I think what my main point was that Chenkai's Coulomb blockade did not have self energy, so there it always increases. But there are two more things to keep in mind, though. Depends on whether the Mairana oscillations decreases or increases. It depends on two competing factors. I mean, the superconducting gap is the parent superconducting gap is decreasing, so that tends to suppress the Mairana oscillations. But at the same time, the topological gap is decreasing, so that tends to increase the Mairana oscillation. So which way it's going to go sort of depends on parameter charts still. But the other part is that the oscillations that you see in, so this is where the Coulomb blockade part comes in. The oscillations that you see in the Coulomb blockade are not necessarily the oscillations in the spectrum. So this is why you need a Coulomb blockade calculation, and you can't just take the spectrum calculation or the normal non-Coulomb blockade conductance calculation and just transfer it.
I see. Thank you.
Yeah.
Is there any more question? So maybe I can ask a question, but
oh yeah, thanks.
I'm not an expert in the Mairana.
Well, that's I'm hoping to have discussion outside with not experts in Mairana. I mean, Heining and you and Shankar already know all this, so there's no point. Yeah. So others should ask.
Yeah. So I understand that in those devices, every single detail counts. So, but if we just assume very simple-minded, like a thought experiment, what would be the signature one should do for confirming the Mairana zero mode?
Yeah,
like, for example, like it is possible to do some more like a nonlinear measurement, like a nonlinear IV. I don't think that's the right answer, but I'm just curious.
No, so thanks. No, that's actually exactly, so this is why, I mean, I think theory is still needed. But I think unfortunately, and I think this is true in other cases in more mature fields as well, that the theory needs to sort of be in some kind of coordination with some sense of experiments. I mean, there are. A few years ago, you could just write a paper on an abstract measurement and that would catch attention. Now that's not so much the case. But on the other hand, if you have a good idea and experimentalists do it, then you actually have a chance of having a real impact. As much as physicists have a real impact. Actually, let me quickly, sorry, just if I may, let me actually just, actually, this is, I have a slide from Colloquium that I gave that might be slightly better for this purpose. So just let me just show that slide. Okay, so yeah, so again, so this is again the nonlinear nonlinear kind of the three terminal setup again that I'm showing. This is actually the experimental data that shows some kind of a gap closing. So now I suggested thermal conductance. That actually has a much better signature, but thermal conductance is hard. One can imagine various kinds of noise or noise-related measurements here. And again, some of these have been discussed, but one can, like, for example, some version of noise might be more. So the question is, but they have been discussed, but what has not been discussed is whether they are better indicators of the separating, like the good, bad, and ugly scenarios. So there's sort, for example, yeah, noise would be one situation. So again, my favorite. So let me show here. My favorite really scenarios are some form of interferometry, where you either put the superconductor in a ring, or you have the superconductor and like a normal interferometer here. The picture I'm pointing at right now is an actual experimental device from. Sorry, I don't have the reference here somehow, strangely, which is bad. But I can definitely to share that if for anyone who's interested. Unfortunately, these experiments don't quite work yet, but variants of but people are trying, and they're not completely hopeless. And again, sometimes the first versions don't work, and then later ones work. And then this class of experiments are again sort of more dynamical, like fractional Josephson effect, where you look at the Josephson effect of this superconductor. So I guess the problem is for theorists that a lot of things have been proposed, and a lot of things have been tried and don't work. So which one will work and which one won't work is a little bit harder to figure out. I think one rule of thumb is that simpler is better. So yeah, that's my sort of complicated answer to your question. There's not a clean answer at this point, I guess. But people are trying experiments, so they're yeah. But I'm happy to discuss more. Yeah.
Sure. Thank you.
Sure.
Is there any urgent question?
Let me just make a quick comment since the issue of experiment came up. The Yang's question. So, topological is by far the most active area in condensed matter physics for 15 years now, and it's not decreasing. It may not be increasing, in an accelerated rate, but it's still increasing even within CMTC. Now people are doing flocade topological. I mean, every word that existed in condensed matter now is re-arising with the word topological after that, right? And I'm not being facetious because topological, it's a mathematical thing. Let's ask ourselves this question. Has there been a single conclusive experiment seeing topological effect in anything in the last 15 years? Absolutely conclusive, meaning, topology is a non-local effect and it has to be protected. I can't think of one. There are many that are claimed, and there are many that come out in glossy magazines and often are not reproduced, or later on people write theoretical papers saying, well, no, this is not this is something else. I have written many papers like that. Probably the cleanest papers are probably in nanowords. And I am personally convinced in nanowords, topological Mairana modes have not been seen. In fact, even non-topological on-red mode may not have been seen. It may be all just disorder, but that's a different question. I'm already writing papers on it. But in this context, this morning I was thinking, can anybody tell me an experimental discovery or measurement in last 15 years which decisively saw a topological effect in a solid state system?
Are you topological order or like topological insulators? I mean, surface states, I think they're ubiquitously seen.
No. Seeing just a Dirac cone and claiming that to be topological is not going to work with me. There's nothing topological
like
about
if you see 1 or 3 or 25, I think that's topological.
That's just band structure. You want to call that topological? Fine. I'm not. I want something a bit more serious.
Yeah, that's what I'm asking. So it's topological.
I want something a bit more serious. Right. I want.
Well, and operationally, those are not insulators.
They are not insulators at all. In fact,
they're topological, but they're not insulators.
Let's go slowly. Those
maybe
topological. Look at it. They have a typical 100 millielectron volt energy regime where things are completely vague because of disorder. They come down as a cone, but where it's topological, meaning the Dirac or wild point, there is nothing. It doesn't matter what experiment it is because of disorder. So I totally discard those things. Those are band structure, and we know band structure works. Okay.
What about quantum anomalous Hall measurements? Like
quantum anomalous Hall, let's talk about it. I thought somebody would say that. How protected is that? After enormous amount of work, one saw something a little bit. What that is, you do not know. I put it in the same category. I mean, nobody wrote papers saying, those who are so unconvincing that people don't even write papers saying, what that could be. They're not very protected, and they're not protected even theoretically, right?
Goldhaber-Gordon was like working pretty hard on making the quantization precise in one of these anomalous.
People are making genuine efforts. I have enormous respect for the material scientists, experimentalists, because I know how much work goes into nanoware. But then I realized I should not really be so critical about nanoware. Other subjects are even behind, because there you don't have this amount of money trying to improve materials. So you should be very careful, that topological is a very easy subject now for theories because it's mostly, let's face it, it's mostly free fermion theory, right? And you can do a lot of stuff, but experimental observation with true topological protection and bulk gap protected, all these things have to be seen, right? I would claim to zeroth order, I'm not going to push the thing, it has not been achieved. So, which is, I think we have been spoiled by fractional quantum Hall effect and quantum Hall effect.
Just to add briefly to that, I mean, there's one more issue. I think the standard here is a little bit higher in the sense that there is a very definite, almost, I wouldn't say commercial, but goal of quantum application to quantum computing.
Correct. So that's why I'm not using this system as an example. Here, the standards are very high. That's what I'm saying. Any system.
Right.
And so we should keep that in mind. We know these theories are correct. We know if somebody makes this system, they're going to see what is being predicted because this is band structure theory. But maybe achieving it will take some time. Maybe it's trying to, suppose fractional quantum Hall effect was predicted in 1950s somehow, some genius predicted it. Well, they would have to wait 50 years to see it. So I would say that clean topological effect in the sense you're talking about has not been seen to zeroth order. Anyway, I thought that given the discussion, it's appropriate to make this comment. I'm done.
All right, thanks. Yeah, I'm done.
Okay, so now we are going to the student introduction session.